Imagine a planet, a world of deep, churning water, where the air itself is not the breath of trees but a thick, swirling blanket of pure hydrogen. This is not a concept from science fiction. This is the reality of a world 120 light-years away. This world, known only as K2-18b, is a massive, warm ocean orb where the James Webb Space Telescope has just detected a specific chemical signal with an almost unthinkable probability. The chance that this signal is linked to life, as we know it, is currently registered at 99.7%. For thousands of years, humanity has asked the same question in the silence of the night sky: are we alone? For thousands of years, the answer has been an agonizing, echoing silence. But now, a $10 billion instrument, the most advanced ever built, has delivered a signal that suggests the silence is broken. Yet, here is the cosmic irony, the terrifying twist, that number 99.7%, while sounding monumental to the public, is not enough to convince the rigid, skeptical world of science. It is a whisper when the community demands a shout. It opens the single greatest question in astronomy, while simultaneously refusing to answer it. The molecule at the center of this universe-changing drama is something called dimethyl sulfide, or DMs. On Earth, the process that creates dimethyl sulfide is almost exclusively biological. You find it in massive quantities in our oceans, produced by phytoplankton and marine bacteria as a metabolic byproduct, essentially the breath of the ocean's invisible life. It is such a distinctive signature of life that for decades, scientists have theorized it could be the ultimate biosignature to search for on distant worlds. Before we dive deeper into this mystery, I have a question for you. If we confirm that K2-18b is teeming with life, do you believe it would be simple microbial life like Earth's ancient oceans, or something far more complex? Drop your thoughts in the comments below. I read every single one, and the most interesting answers might get featured in the next video. And if you are the kind of person who loves cosmic mysteries like this, hit that red subscribe button, because what I am about to reveal next will change how you see the universe and the strange warm world of K2-18b. Now, let's go back to the beginning and understand the kind of planet we are even looking at. Our story begins not with James Webb, but years earlier, in the year 2015, with the much less flashy Kepler Space Telescope. Kepler, the great planet hunter, first discovered this world orbiting a distant red dwarf star in the constellation Leo. We knew it was big, about 2.6 times the size of Earth, earning it the label of a super-Earth. We knew it was nestled right inside the habitable zone, the region where temperatures are just right for liquid water to exist on a surface. But that was about all we knew until the most powerful eyes in space turned their gaze. The initial findings were exciting, confirming the presence of water vapor in the atmosphere. This alone made K2-18b an immediate priority target. Yet, new research revealed a structure far more bizarre than a typical rocky world. This is not Earth 2.0. This is what Professor Nikku Madhusudan and his team at Cambridge University call a Hycean world. The term Hycean is a combination of two words, hydrogen and ocean. A Hycean world is theorized to be covered by a vast, hot water ocean beneath an incredibly thick, hydrogen-rich atmosphere. On this planet, the pressures are immense and the heat could be high. Scientists now believe that the deepest parts of this ocean might be a high-pressure, supercritical liquid, where the lines between liquid and gas blur. It's an environment that seems alien, yet it possesses the two fundamental ingredients for life, a solvent in the form of water and an energy source from the star it orbits. But the real breakthrough, the data point that set the world on its head, came when James Webb used its near-infrared spectrograph to dissect the light filtering through K2-18b's atmosphere. This process is like identifying a person by their shadow, only instead of a shadow, it is a chemical fingerprint of absorbed light. The telescope's sensors successfully identified methane and carbon dioxide, the basic building blocks of many planetary atmospheres. But then, there was the extraordinary detection of dimethyl sulfide, DMs. By the way, something amazing is happening in the comments section. Last week, one of our viewers asked an incredible question. If a planet has a hydrogen atmosphere, would the life on it have larger eyes to capture the dimmer light of a red dwarf star? What do you think? Let me know below. The best comments get pinned, and I might even make a video answering your question. Now, here is where things get really strange, and where the mystery of the 99.7% certainty truly begins. The mere existence of dimethyl sulfide on a distant exoplanet, a world so far away that our light from it is 120 years old, immediately opens two impossible questions. First, can we be certain that this molecule is there? And second, if it is there, can it be produced without life? The 99.7% number is the result of statistical confidence, known as a 3 sigma detection. It means there is only a 0.3% chance. The detection is a fluke, a background noise error. That is incredibly strong data. But for science to proclaim a discovery of alien life, the gold standard is a 5 sigma detection requiring a confidence of 99.99999%. The difference between 3 sigma and 5 sigma is the difference between a strong hint and a definitive, world-changing announcement. The data is yelling, but it has not yet passed the ultimate peer review threshold. The problem, the reason this detection is not yet a definitive proof, is the question of alternative chemistry. Dimethyl sulfide is not impossible to produce without biology, but it is extremely difficult. Scientists have scoured the literature for non-biological processes that could create such a distinct DMS signature on a Hycean world, perhaps through strange geological activity or high-energy atmospheric reactions. So far, no known natural, non-living process can account for the sheer quantity of dimethyl sulfide detected. If life is not making it, then an entirely new kind of planetary chemistry. One we cannot yet conceive must be at play. We are left with two options, and both are equally mind-blowing. Either this is the first life, or this is the first glimpse of a totally new form of planetary physics. We left off staring into the vast hydrogen-rich atmosphere of K2-18b, caught between a 99.7% certainty of life and the near impossible standard of a 5 sigma scientific proof. The mystery is less about what we see, and more about the fundamental processes that allow us to see anything at all at a distance of 120 light-years. The sheer audacity of the James Webb Space Telescope's accomplishment here cannot be overstated. We are detecting trace amounts of sulfur molecules in the atmosphere of a planet we cannot directly image, which is orbiting a star that is essentially a cosmic candle 120 light-years away. To understand the deep dive into this biosignature, we must first understand the mechanism. Transit spectroscopy. K2-18b passes directly in front of its star, a dim red dwarf, and as the star's light skims the planet's edges, the atmosphere acts like a prism, absorbing specific wavelengths. Each chemical element and compound has a unique absorption fingerprint, a specific set of colours it steals from the light. James Webb's near-infrared spectrograph is the ultimate chemical detective, precisely measuring which tiny bands of light are missing. It found the deep, clear troughs of methane and carbon dioxide, confirming the atmospheric composition, but the detection of dimethyl sulfide, DMS, was a shallower, more tenuous dip in the spectrum, yet one that appeared with that high 3 sigma certainty. This is the ultimate needle in a haystack detection, suggesting a concentration of the gas thousands of times higher than what is found in Earth's own atmosphere. The detection of high levels of DMs is compelling precisely because of the known chemistry on our own planet. Here, DMS is the signature of the marine world. It's a waste product that helps phytoplankton, the microscopic plants of the ocean, regulate the salts in their bodies. When they excrete it, the gas wafts up, giving the air a distinct sulfuric smell, often noticed as the scent of the seashore or the telltale aroma of low tide. If K2-18b is indeed a Hycean world, completely covered by a deep hot water ocean, then the detection of DMS is perfectly consistent with a planet teeming with a vast, thriving ecosystem of alien phytoplankton. The theory suggests a world completely unlike Earth in surface conditions, yet familiar in its underlying biology. The life on K2-18b would have to cope with a powerful gravitational field being 2.6 times Earth's mass and a potentially high-pressure, high-temperature ocean. Yet, the vast, stable body of water and the constant, albeit dim, energy from its red dwarf star create an ideal environment for life to originate and flourish. This could be a world perpetually stuck in Earth's microbial past, resembling our planet not today, but 3 or 4 billion years ago, when our own oceans were first bursting with invisible organisms. If this information blew your mind, hit that like button. It tells YouTube's algorithm to show this video to more curious minds like yours. Together, we're building a community of people who aren't afraid to ask the big questions. And trust me, what I am about to tell you next about the scientific debate surrounding the nature of this life is even more mind-blowing. While the evidence for a biological source is extremely strong, the scientific community maintains a necessary level of skepticism. This is where the competing theories and the truly strange possibilities of non-biological chemistry come into play. Professor Madhusudan, the lead scientist, is careful to note that they cannot, with 5 sigma certainty, rule out non-biological processes. The 2 main areas of doubt center on geology and extreme physics. One school of thought suggests that the dimethyl sulfide, or molecules like it, could be generated deep within the planet's mantle and then vented into the atmosphere through volcanic activity or hydrothermal vents. However, for a Hycean world this is problematic. The immense hydrogen atmosphere would require an equally immense and continuous geological source to pump enough sulfur containing gases into the upper atmosphere to match James Webb's readings. We do not know of any known geological process that could sustain that level of output on a water-heavy super-Earth. It would imply a planetary chemistry completely divorced from the internal dynamics of Earth, a chemistry of extreme, continuous planetary venting. The other major theory is the possibility of contamination or misidentification. Skeptics point out that the dimethyl sulfide signal is close on the spectrum to other more common, non-biological sulfur compounds. Could James Webb have simply misread the subtle fingerprint? While the Cambridge team has performed rigorous tests, there remains a tiny possibility that the molecule is not DMs at all, but some other, simpler sulfur compound, whose presence is entirely non-biological. This is the core reason for the need for 5 sigma confidence, to absolutely eliminate the possibility of a non-biological, non-living origin for the molecule. This entire situation has sparked intense debate, even a kind of cosmic political rift within the scientific world. On one side are the optimists, like Professor Madhusudan, who state that given everything we know about this Hycean world, an ocean teeming with life is the scenario that best fits the data. On the other side are the traditionalists, who demand an explanation that is 100% non-biological, however exotic, before conceding the existence of alien life. This debate itself highlights the profound, paradigm-shifting nature of the K2-18b discovery. If we confirm life here, it would confirm that life is not rare, but common throughout the entire galaxy, meaning the universe is biologically prolific. If the DMS signal is indeed confirmed as a biosignature, it will force us to fundamentally re-evaluate the entire concept of the habitable zone. K2-18b is orbiting a small, dim red dwarf star, which are the most common type of star in the universe. If these Hycean worlds, which are also thought to be incredibly numerous, can support life, then the number of potentially living planets in the Milky Way skyrockets from the billions to the tens of billions. The vast, cold, dark cosmos suddenly becomes an astonishingly crowded place, filled with warm, watery, hydrogen-enveloped worlds. The question is no longer whether we can see dimethyl sulfide, but what the existence of this potentially biologically common world means for the fate of every person gazing up at the night sky. The discovery on K2-18b forces a powerful confrontation between cold, hard science and deep-seated human philosophy. For centuries, the idea of life beyond Earth was a matter of speculation, theology, or science fiction. Now, we are standing on the precipice of transforming that eternal question into a solvable scientific problem. If the DMS signal on this Hycean world is confirmed to be biological, it moves life from a miracle unique to Earth to a cosmic imperative, a natural outcome of planetary chemistry whenever the conditions of water, energy, and time converge. This fundamentally alters our place in the universe. If life is common, then the most profound implication is that the long, improbable chain of events that led to our existence was not the result of cosmic luck, but of cosmic law. It suggests that the emergence of simple life is perhaps inevitable. It replaces the deep, existential dread of cosmic solitude with a universe that is vibrant, full, and biologically active. It means we are not alone. It means we never were. The philosophical implication of a Hycean world being the first confirmed home of alien life is particularly significant. Hycean worlds are fundamentally different from Earth. They are hotter, heavier, and swathed in hydrogen. If life can thrive in an environment so physically distinct from ours, then the constraints we place on the concept of habitability must be immediately expanded. We must stop searching for Earth 2.0 and begin accepting that life is infinitely more adaptable and resilient than we currently give it credit for. It means our galaxy could be full of worlds we previously deemed barren, simply because they did not look like our comfortable blue marble. What we've covered today is just the beginning of a much bigger story. Next week, I am releasing a video about the possibility of exotic life forms that could exist without any water at all, and the findings based on new research into methane worlds. Absolutely shocking. Make sure you turn on notifications so you don't miss it. Click that bell icon right now, because the universe still has so many secrets to reveal, secrets that challenge the very definition of life itself. Looking to the future, the work on K2-18b is not complete. The scientific community has a clear goal: achieve that 5 sigma detection. To do this, Professor Madhu Sudan's team has requested further observation time on the James Webb Space Telescope, perhaps 16 to 24 hours of additional, focused spectral analysis. This future data will use different instruments on the telescope, allowing them to cross-verify the DMS signal against other potential contaminants and eliminate the last remaining non-biological explanations. This is the final scientific mountain to climb before the greatest announcement in human history can be made. The impact of confirmation would extend far beyond the astronomical community. If life is common, the search for intelligent life, or technosignatures, will suddenly gain an overwhelming urgency and justification. Why spend billions searching for intelligent signals if life is a fluke? But if life is common, then intelligent life must also be common. The focus of groups like SETI, the search for extraterrestrial intelligence, would sharpen immediately, prioritizing the Hycean worlds and their myriad red dwarf suns. The entire trajectory of our civilization, from technology and philosophy to religion and culture, would be changed forever by a single definitive spectral line. Ultimately, the story of K2-18b is the story of human capability. 100 years ago, we did not know exoplanets even existed. Today, we can analyze the breadth of a distant world, 120 light-years away, and stand a mere fraction of a percent away from solving the greatest riddle of existence. This journey has not only revealed the subtle complexity of alien atmospheres, but has also showcased the immense power of our scientific instruments, the incredible $10 billion eye we sent into space. The James Webb Space Telescope has given us the capacity to ask, and perhaps even answer, the $10 billion question: are we alone? The latest, strongest evidence says no. It says that out there, on a massive humid water world orbiting a tiny star, the biological processes that started here on Earth may have already begun again, totally independently. It means that the universe is alive. So, what is your answer to that question? Do you believe the dimethyl sulfide on K2-18b is non-biological? Or are we truly on the verge of confirming the first alien ocean, teeming with life? Drop your thoughts in the comments. I can't wait to read them. And if you enjoyed this deep dive into K2-18b, you'll love my video about the terrifying mystery of dark matter. It explores the composition of 95% of the universe from a completely different angle. The link is in the description, or you can click the card appearing right now. Until next time, keep looking up.